Okay, thank you very much, Chairman. So this is experimental work, mostly experimental work, done also in collaboration with different theoretical groups, including Yaroslav Fabian, Igor Zutic, and samples have been grown in collaboration with a group of Michel Pen and Korean Tucson, and the main part of the work is done by my PhD students, Cesar Gonzalez Rolano, Diego Paso, and beginning part by Isidoro Martinez in Universidad Autónoma de Madrid. So basically we are looking for next generation of dissipationless structures, and joining spintronic and superconductivity is one of the way which gives rise to superconducting spintronics. And so far, mostly the system which have been studied were the system in which is we have created kind of spin valve and the change exchange field to change the critical temperature, for example, or also penetration of triplet Cooper pairs into the ferromagnet with non-collinear magnetization has been investigated. Here we have a review. Also, recently a reciprocal effect when the superconductivity affects the ferromagnetism by changing its magnetic crystalline anisotropy has been predicted. Also, before it was such effect was mainly restricted to restructuring and pinning of domain wall and Meissner screening. So our work is basically the first experimental study of fully epitaxial superconductor ferromagnetic structures, which are coupled through a spin-orbit coupling, Rarba type of spin-orbit coupling, and also there is a symmetry filtering, and basically, as I will show, symmetry filtering in the presence of spin-orbit coupling allows us to introduce the current, which is mostly affected by the presence of spin-orbit coupling. Also, the system which we investigate has a luck to create non-volatile magnetic states. So, due to this radial spin-orbit coupling, also, which allows to investigate superconductivity in vanadium and the different orientation of the ferromagnet, and all this without any external magnetic field. Very recently, we have published just a couple of days ago, it was published in Advanced Electronic Materials, also normal state properties of the system show amazingly high magnetic tunneling magnetic resistance at very high electric fields. So basically, also due to our spin-orbit coupling, we are able to create high bias, very sensitive magnetic field sensors, for example. And to the proof of presence of long-range penetration first initially was indicated in this publication by studying zero bias anisotropy of the conductance. And recently in these two publications, we also found in-plane, change of in-plane and out-of-plane magnetic anisotropy induced by the superconductivity. So it was recently predicted that not only magnetic textures, but spin-orbit coupling itself also could be additional source to create long-range penetration of the triplet components into ferromagnet. And here is a work by Sebastian Bergeret and Farkhad Aliev, where it is clear seen that depending on orientation of exchange field and ferromagnet, we can have or not long-range penetration from superconductor to ferromagnet. And this is inversely proportional to temperature. So it's really effect which is just restricted to the decrease of TC. So there were different proposals to detect this effect, starting from paper by our collaborators, Petra Fogel and PhD student from et al. From group of Igor Zucic and Fabian, and other publications. Also, there were application prediction for anisotropic Meissner effect and critical temperature anisotropy. So our main proof comes from this observation of the magnetanisotropic zero bias effects in this structure. As I mentioned, also inverse effect has been also predicted, that system which presents coupling between superconductor and ferromagnet, so spin-orbit coupling in the deeply in superconducting state may suffer a change of in-plane anisotropy if the system is fully epitaxial, and also out-of-plane anisotropy. So, for example, for in-plane anisotropy, below TC, the hard axis 110 can become dominated, and out-of-plane anisotropy also will be stimulated, depending on the conditions, of course, of competition between in-plane and out-of-plane anisotropy, which are considered in our case experimental. So the system which I mentioned is fully epitaxial, first fully epitaxial example of coupling between superconductor, vanadium cubic system, and the cubic iron, but the band structure in cubic iron is very much different from the band structure in vanadium. Actually, the main difference is that delta 2 symmetries present in vanadium are absent in iron, while delta 1 symmetry, which is provided, which can tunnel very effectively through MgO, is absent here. So the main, so basically, theoretically, if you put in contact with a spin-orbit coupling these two materials, there will be no current at all. And only presence of spin-orbit coupling, which is able to change symmetry and mix different symmetries present in iron and create delta 2 symmetries, for example, is capable to create current channel. So all current, basically, which we will be investigated, is current of the electrons which suffered spin-orbit coupling. And indeed, we see that if we have control sample, for example, vanadium MgO gold, it's highly conductive tunnel junction. While if we just introduce the interface between vanadium and iron, the conductance drops 2 orders of magnitude. If we introduce two interfaces, it will be further dropped. So this is vanadium sandwiched between two iron layers. If you see on the IV characteristics, you will see that conductance is quite small, and then this is evidence for some band structure features. And all current, as I mentioned here, is due to spin-orbit coupling. This effect, briefly just mentioned, the effect of the huge change of the conductance of this vanadium MgO iron system under applied bias gives rise to the very amazing effect of very high TMR at high biases. So basically in the control system, the iron MgO iron, the low bias TMR is bigger, but at above 0.5 volts, the tunneling magnetic resistance in these structures can be very much higher than in standard structures. And we published this recently, and we also have the patent application for these structures. The presence of spin-orbit coupling can be tracked also by changing, for example, by studying out-of-plane above gap conductance anisotropy. You see that this was done in this publication, so we tracked presence of spin-orbit coupling, but also this is a well-known effect from DFT calculations, and basically perpendicular magnetic anisotropy in iron MgO structures is due to radial spin-orbit coupling, and this effect is used in all your computers because this is standard magnetic tunnel junctions sensors of hard disks. But if we create, so basically perpendicular magnetic resistance is present in very thin iron layers at room temperature, but in our structures we tuned thickness to about 10 nanometer, where depending on the field history, we can create or in plane or out of plane magnetization. And actually this is a sketch which is shown here, and this paper explains how to create different non-volatile magnetic states in the system, or in a ferromagnet in contact to superconductor through the spin orbit coupling. For example, this is out-of-plane magnetization tracked through tunneling magnetic resistance. You see that we can enter in a perpendicular magnetic state, skip the field, and we can keep system out-of-plane magnetized at low temperatures. While at room temperature, we just have we don't have the non-volatile perpendicular state, but at low temperatures we do. And from these different magnetic resistances in plane, out of plane, perpendicular, we can extract spin polarization. Effective spin polarization of iron here is around 0.7. As I mentioned, the first indication of the possible long-range penetration was done in this paper, where we investigated at zero applied magnetic field depending on orientation of the iron respect of in plane and out of plane, and we observed about 15% of tunneling magnetic resistance at zero bias, and we assigned this to magneto-anisotropic contrary reflection predicted by theorists, and this was the first indication of possible long-range penetration of Kuiper-Pearson in iron. In the presence of external magnetic field, of course, there are vortices formed in the system, and here this is fitting of the results to the theory modeling, which takes into account also presence of vortices. Interestingly, above we observe resonance enhancement of the conductance, which is basically a kind of quantum well states formed in the iron, and these states are formed mostly below critical temperature, and this is the amplitude of these resonances, which are kind of Macmillan resonances, depend on the orientation of the iron, hard and soft layer, and basically this relative orientation of the soft layer controls the magnitude of this resonance. Okay, so before the similar effects were observed without application of our magnetic field in these papers, and were linked to equal spin and rate reflection. Well, now let's turn to the second part, which is demonstration of the influence of superconductivity on magnetocrystalline anisotropy. The system is perfectly crystalline, so if we obtain a magnetic field in plane, so we see perfectly transitions. We have a second layer which is fixed, and the soft layer rotates. We see transition between parallel, perpendicular in plane, anti-parallel, again perpendicular, and vice versa. So all this in the normal state. But in the superconducting state, when we rotate the magnetization, we observe the appearance of the new states which correspond to the hard layer, hard direction, and we analyze this by making histograms depending on if we start rotation in the anti-parallel state or from the parallel state. We see more or less clearly, because here if we pass to anti-parallel state, probably domain walls are formed before. But clearly we have a shift from the reference easy axis into the new easy axis, which is p/4 oriented respect the main axis. Yeah, and this happens in a superconducting state. You see that the amplitude of the probability to find system in new orientation increases below critical temperature. Also, we analyzed the possible effect of Meissner screening and interaction with domain walls, which was previously reported before. And here you see that, for example, this is possible effect of Meissner screening. The change of soft layer coercive field is only below 10%, which is quite small and does not affect our effect. Hard layer switching field doesn't change at all. So in our experiments, these changes of Meissner screening introduce only 10% correction to the effect. We analyzed numerically also possible vortex domain wall interaction by calculating stray fields which affect superconductor, by mapping the words in superconductor and calculating the interaction energy between these stray fields and domain walls. And our conclusion was that if there is any interaction, it will be more stronger for interaction along easy axis, but not along hard axis. So, and this contradicts to the change of the easy axis from to the new hard axis. So it would be vice versa effect would stabilize further the easy axis direction 100.
Mikhail, sorry to interrupt me. 5 minutes including questions.
Okay. So I move very quickly. So skip this, and our model basically is the following here: that triplet Cooper pairs are generated in the system. Also, we have introduced modeling made by coupling group, also weak antiparallel coupling, and new minima appears in free energy. And to compensate generation caused by triplet Cooper pairs, system moves to the new local minima along 100 and changes magnetocrystalline anisotropy by this way. Also, we can even observe the orientation 45 degree at zero field, spontaneous orientation. But this is observed some in intermediate temperature. So our experiments also show that change of magnetocrystalline anisotropy and due to the spontaneous rotation of magnetization. And finally, we very recently show experimentally that other effect predicted by theories that out-of-plane anisotropy also could be affected by superconductivity also take place. For example, here you see that out-of-plane field changes dramatically by the sample 10 by 10, but for the samples larger, big effect is seen, and we attribute this to competition between in-plane and out-of-plane anisotropy. Here, the right slide shows how the zero field angle of the soft layer changes. You see that it becomes trend to be perpendicular for the samples, smaller size samples. And the very last slide, the effect is affected also by presence of electric field, and the bigger effect are observed in the smaller size samples where the out-of-plane anisotropy is larger. So I conclude here that we present the first experimental study of epitaxial ferromagnet superconductor spin-orbit coupled junctions. Different non-volatile magnetic states could be created in such system for in-plane and out-of-plane anisotropies. Systems are important for application because they have very high bias tunnel magnetic resistance, and zero bias conductance anisotropy and superconductivity in exchange of magnetocrystalline anisotropy points towards the effect of Radsby spin-orbit coupling induced long-range penetration. And finally, we are also now investigating short noise in the system. This is paper in preparation because as transport is mostly controlled by spin-orbit coupling, we see experimentally that this will also produce very unusual results for the short noise. And the system is the first experimental system in spin-orbit coupling, superconducting spintronics, which is very close to application because it is based on well-known MGO structures. Thank you very much for your attention.
Okay. I wanted to ask you a question regarding this. Have you thought about sandwiching this vanadium between the two ferromagnets? So you make a sort of pseudo-spin valve and check what is the change in TC that you get when you measure across the transitions.
Yes, exactly. We have these structures. We haven't just studied yet, basically, but we are having found these structures. And next, I showed just quickly some results when these kind of experiments were done. Exactly the structure which you mentioned. This is here. No, this is different. But actually, yes, we have these kind of structures, and this is work for next PhD student. Let's say we just didn't have enough hands to investigate. But you're right. This should be investigated.
Yeah, because presumably it's quite large. But yeah. Okay.
Mm-hmm.
Go on.
Can you study also the Dzielashinsky-Murray interaction induced by the superconductivity?
Well, here we have fully epitaxial structures, and Rashba is the main source for spin-orbit coupling. For Dzielashinsky-Murray, you probably need other structures like platinum, etc. So it's
no, Rashba is enough.
Yes, Rashba also, but let's say the typically the let's say Dzielashinsky-Murray interaction in such a fully epitaxial structures. I should think of mostly Dzielashinsky-Murray is obtained in not fully epitaxial structures where you have interface disorder, etc. As far as I understand.
Okay, thanks. But just our work, recent theoretical work, show that these are just they come from the same source, the correction to the anisotropy and the Dzielashinsky-Murray.
Okay, maybe we can open your papers and discussion.
Yeah.
Okay,
So,
thanks.
so